And I'm going to talk in general terms about polymers, and I'm going to talk a little bit about the resources topic, which has got some polymers stuff in it too. And I'm going to talk then in detail about polymers, structure and structure of them and how they form and all sorts of things like that. So some of this stuff we may have done when we're doing the resources topic, but I don't honestly remember, so we're just going to make sure we've covered it. So first thing you need to know is that polymers are essentially long chain molecules. I'm going to go about what they are and how they form a bit later on. If you can sort of imagine them as long chain molecules like that, big long chains often of carbon atoms joined together. Okay, they're made from monomers joined together, so lots of molecules joined together to make one long chain molecule. So we call lots of monomers individual monomers, and polymers the long chain you make from it, right? And you've seen these in biology, you've seen these in, I think we've seen these in chemistry before, but you need to know that the properties of the polymer are very different from, but related to, the structure of the monomer. So the monomer will typically be maybe a low boiling point liquid, something like that, but the polymer might be quite a high, a relatively high melting point solid, because you've combined all of those molecules together to make a very long chain molecule. You need to know that one of the most important polymers is polyethylene, and we'll look at the structure of that in detail in a bit, but it's made from the monomer ethene you know how to draw, right? And you need to know, for the resources topic, there's two types of polyethylene. We've got low density polyethylene, so I'll write that out fully as well. And there is high density polyethylene, but we'll come to that in a second. Right, so we'll do low density polyethylene before. I don't think you really need to, I'm going to double check this, but I don't think you really need to know exactly the conditions that they're made and how they're made differently. But low density polyethylene ends up having structure like this, where the polymer chains are kind of sitting in a kind of untidy pattern with kind of gaps between them, not very well closely packed. So the language we're going to use in exams is not closely packed, not in a very regular structure, is it? And that's because these molecules have what we call branched chains. Okay, so rather than just being straight lines, they're branched and they come off in all funny angles. Okay, it's got branched chains, chains of polymers that are joined together. And obviously by its name it's a low density and is used for slightly different things than high density polymers. Well, so that might be the sort of thing you get in a kind of plastic bag that you use for shopping, right? So high density polyethylene is made under slightly different conditions, still with the monomer polyethylene, and that's the high density version. Right. So instead of having branch chains, which are caused by the conditions that it's done in, if you do it under these slightly different conditions, it says it's slightly raised pressure and at 50 degrees, but the details of that you need to know. But the packing is completely different. So these are straight chain. We draw them as zigzags like this, and you'll see why at different time. But instead of being all over the place and branch structures, they might be something like this. So they closely pack the polymer chains to each other, which means they take up much less space per polymer molecule, which means that they have much higher density. Okay, so that's HDPE. And so the conditions that you combine the ethene molecules, ethene monomers together, determines their structure, and the structure is linked to the properties, and the properties are linked to the uses. That's what I'm trying to get at here. Okay, So some polymers are high density and some are low density. That's it for that. It's very typical of the resources topic, some slightly random facts joined together. What I think is slightly more chemistry related and actually related to biology as well is that some polymer chains can be cross-linked and sometimes they're not. So if you think of a polymer just like that for a minute, it could be, and maybe some have got chains going across like that, but you can have polymers that are not connected to each other, a bit like, so when you cook spaghetti, you kind of get all the spaghetti floating around, and let's say you drain off the water, that spaghetti, kind of wet spaghetti moving around in the pan, is kind of what that like is what I want you to think that as being looked like. Wet spaghetti. Now I'm going to have to spell spaghetti. Hopefully that's right. So that's like wet spaghetti, all sort of sliding past each other, all that kind of stuff, right? When you cool that down, and let's say you left that pan of wet spaghetti to cool down, it would kind of harden, and it would kind of form a kind of a lump, right? That was what we might call something called a thermosoftening plastic. Or thermosoftening polymer. The word polymer and plastic are essentially the same thing. Okay? The thermosoftening polymer. The thing about thermosoftening polymers is you can heat, remold, I should know if mold has got an U in it or not. I think it does. And reset. So you heat, remold it, cool it down again, and it resets. And so you can that's how you can recycle plastics, right? So if I chuck in my plastic water bottle that, remember, lovely Esther was holding last week or last lesson, you chuck that in recycling, heat it up, melt it, turn it into something else, right? So that's thermosoftening plastics, which look a little bit like wet spaghetti, particularly when you heat them up. Okay. The thing about the polymers that I'm drawing now on the right-hand side is that some clever chemistry has been done to cross-link the polymers. And this happens in biology too sometimes. So sometimes in biology you can have polymers that are cross-linked. So the polymer chains are long and going left to right, but there's links together. And this is what we call thermosetting polymers. And the one on the left here, there's lots and lots of molecules, lots and lots of spaghetti chains, if you like. On the right-hand side, because they're actually covalently bonded together, they're held together with strong bonds, it's one giant molecule. So any Formula 1 season's about to start. Anyone into Formula 1 at all? Or into cars at all? Well, you all know what tyres are, at least. Tyres are essentially one molecule, one long molecule they're all joined together with these covalent bonds. So thermosetting polymers. Now they're great. They've got some really important and useful properties. For example, they have high melting points and quite strong resilience. The problem is you can't recycle them because you can't melt them down and turn them into something else. So cross-links is the key word there. So cross-links between chains. Okay, cross-links between chains. Now let's go through that in a little bit of detail. Between the chains here, rather than bonds, these are molecules, right? So what's going to be the weak force between these molecules? What's that going to be called? Hands up on that one. Yeah, good. So they are weak, I'm going to say relatively weak intermolecular forces, which is why they can be broken easily or overcome really easily and reformed and remolded. Whereas the cross links are covalent bonds. We're going to put strong there. Strong covalent bonds between the polymer chains. And they can't be remolded or can't be remolded, and therefore can't easily be recycled. So it will not soften. Eventually, so if you heat it up, if heated, it will, the word in the book is char, essentially burn, eventually catch fire. So you can't split the polymers apart from each other. And an example of use of that might be tyres, highly resilient, highly strong, stable, no problem at all. And the one on the left here might typically be sort of plastic bottles that you can anything you can recycle. Right, that's your basic resources a bit about polymers. We'll come back to the resources topic because obviously it's an important one. But we're now going to get into the nuts and bolts of the organic chemistry here now. Okay, so don't overlook this stuff. This is paper 2, so I know it feels a way away, but don't overlook this important stuff. Okay, I'm going to start a new page. Feeling wild and crazy. Right, so addition polymers we're going to talk about to start with. Now you might remember we talked about the word addition reaction in chemistry before. When we were talking about a certain type of molecule, I made some joke about 2 becomes 1. What type of molecules can undergo addition reactions? Just tell the person next to you. You remember when you take one molecule, add it to another, you form a new molecule. So 2 molecules become 1. What molecule was it that we can do that with? Okay, shout it out in 3, 2, 1. Good, yeah. You didn't sound very sure what you said. So good. So this is when you take typically alkenes and react them together. There are other examples than alkenes, but for GCSE chemistry, addition polymers applies only to alkenes. And the simplest example of that would be the reaction of ethene. We all know how to draw ethene, something like that, right? The double bond here is really important because the double bond allows the chemical reaction to take place. Because this alkene, this molecule, is unsaturated, it can become saturated by undergoing chemical reactions, undergoing addition reactions. Now, if you put it under certain conditions that you don't need to know, happily, it will undergo a process called polymerisation. Right? It will turn in from a single monomer, like little individual monomers that we draw on the previous page, that will turn into one long chain. The way that it does that, I'm going to draw for you, but I don't want you to copy because it will be pointless and take forever. But then I'll show you how we represent it in an exam. So I'm going to try and make it make sense to you by drawing it for you. I sometimes do this with molymods, and we might in another lesson, but I actually quite like doing it 2D with pen. It sometimes makes more sense to people than the balls and sticks. Right, so there we go. So there's 3 ethene molecules. What can happen is if I add a magic chemical to this, one of these bonds, or this double bond here, can be taken away, right? It can disappear and can be made a carbon-carbon single bond. You end up, by the way, with something hanging off the end, but don't worry about what that is or how that works. So that causes, this green blob here causes this bond to break, because carbons can only make 4 bonds, 1, 2, 3, and we've got a new one there. So what happens is this becomes a bond between that carbon and that carbon of a neighbouring ethene molecule. See how they're now joined together with a covalent bond. But that causes this bond to break and causes a new bond to form here, which causes that bond to break, which causes a new bond to form. And that goes on for maybe hundreds and hundreds and hundreds of molecules of ethene, going from one small ethene, or one group of small molecules, to one long chain of molecules. Now, the way that we represent that, there's 2 ways of representing that. You can either represent it like this, which is my preferred way, but you need to do both. So what we do is we draw what's called the repeating unit. So the thing that repeats again and again and again, hundreds and hundreds of times, is that unit there, which is exactly the same look as the thing on the left. What's the difference between the thing on the left and the thing on the right? And that sounds like a silly question, If you can remember this, this will help you no end with all the more difficult ones we're going to do. What's the difference between those two? Just tell us, someone next to you. What's the difference between them? There's no double one's gone, and we've now got a single bond here. Instead, what have we got? We've got another bond on either side, exactly that. So what we say is, however many of these there are, let's say there's 100 of these, but we're going to represent that with the number or the letter n. There would be 100 of these in a chain, right? So we must remember the little n there to draw it. So that's how we show polymerization. Now, because this is an addition reaction, just like the addition reactions we did with alkenes in the previous lesson, the atom economy here must be 100%, right? Because there's no byproduct. It's just the molecules falling, joining together. 100% atom economy. These are the kind of details I expect you to know if you want to get those with top marks, by the way. Atom economy, because there's no byproducts. I did say there's a, I should say this is called a monomer. This is called the repeat unit. So can you label that repeat unit? Probably better above. Can you put a, sort of highlight that as a key thing you need to know? That's the repeat unit, and that's the monomer. We'll do a few of these, so don't worry. It's not clear yet. The other way of drawing this is sometimes the exam board say, can you show 3 repeat units of the polymer from this monomer? So you basically have to draw that 3 times. That's it. So I'm going to just do that now, show you. So this is 3 repeat units joined together. So how many carbons will there be all together? Show me with fingers. How many carbon atoms will there be all together? Yep, so we draw 6 carbons. 1, 2, 3, 4, 5, 6. And we just draw a hanging bond at either side, just to show that that chain continues. And every carbon makes 4 bonds. There's a hydrogen in each, or 2 hydrogens off each carbon, but that chain would continue. It doesn't stop there, it would continue for maybe 100 carbons before you got maybe a green blob on that side and another blob on the other side to kind of stop at the end. So we don't need to know about that chemistry. Okay, that's it. So this is one of the hardest things of the whole course people find. If you're getting it, we're doing okay. But that's not the only monomer that we have to consider. We have to consider other monomers. But it's exactly the same process. Promise you, it's exactly the same process every time. I will catch you out. I'll deliberately catch you out, some of you. But I'm going to try to catch you out, and you're going to try to watch out for being caught out, and you're not going to be caught out. Right, just warning you. I'll tell you when I'm going to do it as well. Right, so what's the process? This stuff is called chloroethene. I'm really sorry, I should have said that this stuff is called polyethene. Said it on the previous thing. It says polyethene. So the polymer name keeps the name of the monomer. Even though it's got no double bonds, we still call it polyethene, right? Which is a bit weird, but that's what we do. So this is chloroethene. What's this stuff going to be called, Julian? What's the polymer going to be called? If the monomer is called chloroethene, what's the polymer going to be called? Nearly. Chloroethene, yeah. Good. And the way that you draw it is exactly the same as we did before. So we just draw the same thing, but without the double bond. Some square brackets, some brackets around it. Difference is this time we've got a chlorine in one of the positions. I've missed something off though that would lose a mark. See if you can find out what I've missed off here that is going to draw a mark. Just tell someone near you to see you all joining in. Go on then, what is it? What is it? Yeah, the letter N. You have to show that there's an N of them. This stuff used to be called in the old days vinyl chloride. So this stuff is also called polyvinyl chloride. You've heard of PVC, right? That's the stuff they make windows out. You know, the plastic frames on windows. PVC, that's what that is. Right? This stuff, polyethene, is what you make plastic bags out of. So you see this stuff all the time. So it's chemistry, it's molecules that you're familiar with. Let's do another one. Let's do this one, you're getting the hang of this now, so I'm going to give you a little bit less help. Can you have a go at drawing what the polymer would look like, the repeat unit, I should say, for this polymer? I'll give you a little head start, then I'll draw it, and then you can, don't draw it, just draw it straight onto your page and correct it if it's wrong. So hopefully you've drawn this, and I can see the people nearest to me have all drawn this spot on, so you draw the same thing. Like that, yeah? This stuff is called tetrafluoroethene. You're unlikely to be asked to name that monomer. If you are given the name of the monomer, you can easily work out the name of the polymer, can't you? Because it's polytetrafluoroethene. Polytetrafluoroethene, otherwise known as PTFE. So anyone who's used plumber's tape, PTFE tape, now you know what it is. Anyone that's ever used a frying pan that's got Teflon in it, that's what that stuff is. That's what Teflon looks like, right? So Teflon makes lots of saucepans non-stick. Right, it's good stuff. Yeah.
You've got to put the brackets around
do a couple more. So here's the one that I'm going to catch you out with. Don't let me catch you out. So I'm going to pause the video. We'll do the catching out on the whiteboards, and then I'll write it up. I enjoyed that because it's the challenge that people face in the exam. So I've deliberately only sort of half fed you information. We're going to go back to these pictures and have a look here. So what happens here, when you go from monomer to polymer, you've got carbon A and carbon B. And you remember when I drew it in rough initially, it was, in fact I'll draw it on here. I'll go back to this picture. Remember this picture I did right at the start? We've got carbon A and carbon B. Carbon B reacts with carbon A, which causes carbon B to react with carbon A, which reacts with carbon B. And then I said, well, that same thing can happen with chloroethene, and we end up with that going on, right? Same thing. And propene, we can also draw like that, right? That's propene, isn't it? So carbon A and carbon B of propene react with each other, which means off carbon A or carbon B, depending on which around you've drawn it, you've got a CH3 hanging off. So you had a really good go at that, and that was I told you it would be a trick question, and it was a tricky question. And so what we do there for polypropene, and I promise you this is the one that's the most likely to be asked in the exam, and will be, for the reasons that you've just found, will often be got wrong. So the best way to draw it is like I've drawn it there. If I'd have drawn it like that in the first place, you probably would have got it right. So the propene molecules go exactly the same. So just off one of the carbons here, you've got a CH3. Now the reason you mostly struggled with it on the whiteboards there was because you assumed that the third carbon must be part of the chain, but it's not, it's a side chain. There's always a 2-carbon unit with whatever's hanging off those units to be side chains on the polymer. Okay, so this stuff is called propene, and this stuff is called polypropene, and you use this to make all sorts of things. So those plastic boxes over there, probably made of propene. Ropes are often made of polypropene. It's kind of a strong, durable plastic, and the nature of the monomer determines the nature of the polymer, although they're quite different from each other. I'm going to do another one. So how about can you have a go at drawing the polymer of that monomer, please? And I'm going to draw a polymer, and you're going to try to draw the monomer from it. And I'll pause the video and check those. I'll do these on mini whiteboards to start with, please, so I can check them. Yeah, so well done, you did that with no bother at all. Don't worry about the names of those, you've got the idea of the naming. And you've got the idea. So just a final little challenge for you. Can you draw 3 repeat units of the one circled there? 3 repeat units of that one on your mini white. So, condensation, polymerisation. Just as a little reminder, while I'm talking to you, this lesson's being recorded for the sake of people not here, but there are a whole bunch of videos on organic chemistry that I've summarised all of organic chemistry in 3 half-hour videos on the website. I will do some other ones that people have requested, but do look out for those. I'll also start doing Friday after school revision sessions starting this week. Okay, so look out for those. I'm going to do a session. I'll advertise it at some point to tell you what's going on. But condensation, polymerisation then, right. So first thing to realise, it's polymerisation, same sort of process, monomer goes to polymer, and it's a condensation reaction, so what's going to be produced as a byproduct? Yeah, so we're going to get water byproduct. But sometimes it's or a similar small molecule. Go find another one. Actually, what you've got with condensation polymerisation, you've got a couple of sort of possibilities really. It could be that you have monomer A and monomer B, and then they join together to form a polymer which is A, B, and so on for maybe 1,000 A's and 1,000 B's or whatever. Or it could be you've got monomer A and it's joined together 1,000 times just like we had before. That's what addition polymers were. You can get either of those scenarios in condensation polymerisation. Okay. And monomer A and monomer B combine together to make a water molecule, right? Just like we learnt yesterday, or whatever it was. And that can happen in a number of ways, and there's no way that I'm going to get through all of this sort of properly and carefully today. We'll practice this another time and finish off what we need to know. But we're going to start off with one example here. So we're going to take monomer A. We're going to say is this molecule. Now the thing about this molecule is that it's a carboxylic acid. Yes, remember we drew those last time, but it's not any old carboxylic acid, it's what we call a di-carboxylic acid, because it's di just means there's 2 of them, one at either end of the molecule, right? That means this molecule can grow in either direction, right? It can grow in both directions. So a single carboxylic acid can only join to one other molecule. This can join in 2 directions. It's like a person with 2 hands. And a nice analogy for learning this is, imagine, I don't need to get you to get up and act, but imagine, let's say I got you, half of you to be molecule A, half of you to be molecule B, and to hold hands with someone either side of you, AB, 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 like that, right? We're going to call that molecule A for now. If that reacts with molecule B, a condensation can take place. Now, what do carboxylic acids react with? We learnt yesterday. We did it, in fact, we practiced it first thing this morning with the mini whiteboards. What kind of molecule do carboxylic acids react with to give esters? Not ethene, no, not, yeah, what is it? Alcohols, yeah. You drew it perfectly this morning, yeah. But instead of any old alcohol, how about we use a di-alcohol? An alcohol with an OH at both ends. So I'm going to have, I'll use that one. So this is monomer B, which is a di-alcohol. It's got a name. We don't need to worry about the name of it. And you know that when you take a carboxylic acid and an alcohol and react them together, they release water, and they do that by losing an H from one of the molecules and an OH from the other, just like you drew this morning. So if we take the OH from here and we lose it, and the H from here, we lose that, and that makes the water molecule. So I'm going to draw that over here as my water molecule that's formed. There it is. This is the reaction. I'm going to draw, because it's so big, I'm going to draw the product underneath. All I've got to do, remember what we did before, was we said, let's draw the carboxylic acid without the OH, draw the alcohol without the H, and clip the molecules together, right? It's not yet a polymer, but it's getting closer to being a polymer. So you draw the carboxylic acid without the OH, you draw the alcohol without the H that's pointing to it, and you end up with that, right? But we join those two molecules together when we make that water molecule there, okay? That's just the same as what we did before. We've just got an extra thing hanging off at either end, yeah? I'll give you a chance to catch up and draw that. Lovely, isn't it? Yeah. Okay, so it's only part of the story. It gets a bit more complicated, but not unbearable. Is that this end of the molecule can grow and extend again. So this is an alcohol at this end. So what can this react with? Shout it out, or tell someone near you. It's an alcohol. So what can it react with? Out of the alcohol and the carboxylic acid, what's it going to react with? It's going to react with the carboxylic acid. So you can stick a carboxylic acid there. This end is a carboxylic acid, so what's it going to react with? Alcohol. So you're going to get A, B, A, B, A, B, A, B, right? Thumbs up, we're getting somewhere, right? The way that you draw that as a repeat unit is as follows. So what you've got to do is, I would draw it like this to start with, maybe in pencil in your exam to start with. And then, when we draw the monomer, we must lose the OH from that end again, and the H from that end again. So we must lose a second molecule of water. And if you can remember that it must be 2 lots of water left, you're in a great opportunity to get both marks here. It's really hard, a lot of work for 2 difficult marks, but I'd love you to be able to do it. There we go. So if I draw that repeating unit now, missed the carbon off. Sorry, there's a shorthand in chemistry that you don't need to draw the carbons that I just started using there without thinking about it, sorry. There's the ester, and if you get 1 mark, if you get 1 mark if you draw the ester. So I lop off the OH from one end and the H from the other end, and I put an N there. So how many water molecules in total have I made through this polymerisation process? 2. So what we're going to write? We're going to write 2H2O. What we're going to write instead? 2NH2O, yeah? So you might get 3 marks for this. 1 mark for drawing an ester, which you can all do because you showed me that earlier on. 1 mark for getting the ends of the molecule right, which is often the bit that people get wrong. And 1 mark for getting 2 lots of water correctly drawn up. And now almost nobody does the water, even though, because you're sort of so busy concentrating on the difficult bit in the middle there, you forget to write the easy bit, the water molecule. So a 1 out of 3 is as good as most people do. Can you do better? Well, possibly. Right. We've got 3 minutes. I think that's a good place to stop, actually. And what I'll do, I'll use the last 3-4 minutes to practice that. We'll do one on the. You can have a go at doing one of these on the mini whiteboards, and then we'll do some more examples and the AAAA type and some different variations of this and some biological polymers next lesson.